Hello everybody and welcome back to another geometry lesson. Today we're going to take a look at section 7.4. Now before we start talking about this, 7.4 and 7.5 are all going to be about the different quadrilaterals. To help us understand this, I have this graphic organizer that I've just made that I'd like you to copy down if possible. We've got different bullet points for each shape that we are going to be filling in. Different facts about each shape, I should say. So pause the video and see if you can copy this down real quick. If we've had a chance to copy this down, we're now going to talk about all the different properties of each of these categories of shape. So starting with quadrilaterals, what do we know? Well, we know that quadrilaterals have 4 sides. So it's a 4-sided polygon. And we also know that the sum of the interior angles is 360 degrees. From here, in 7.2 and 7.3, we talked a lot about parallelograms. And there are 5 things that we know about parallelograms. Because of the definition of a parallelogram, we know that opposite sides are parallel. Because of the parallelogram opposite sides theorem, we know that opposite sides are also congruent. Because of the parallelogram opposite angles theorem, we know opposite angles are congruent. Because of the parallelogram consecutive angles theorem, we know that 2 angles next to each other, which are consecutive, they have to be supplementary. And we also know that in a parallelogram, the diagonals bisect each other. There we go. So when we talk about parallelograms, we're not just talking about the parallelogram that looks like this. Parallelograms can take many forms. For instance, rhombuses, rectangles, and squares are all types of parallelograms. They have opposite sides parallel, opposite sides congruent, opposite angles congruent. All these properties apply. So, because of the flowchart, all of the items down here, so like square, rhombus, rectangle, also fit the criteria of a parallelogram. Let's talk about rhombuses. A rhombus, or a diamond shape, has its own special properties, but it also shares those of the parallelogram. The thing about a rhombus is all sides of a rhombus are congruent. So in this shape, all 4 sides are the same length. Now, there is something interesting that happens with a rhombus, specifically with the diagonals of a rhombus. I'm going to skip over here. If I draw a rhombus, let's say that these side lengths are all going to be about 3, about 3, about 3, and about 3. If I have a rhombus here where all 4 sides are the same, what can we say about the diagonals? I want to draw sort of a dotted line going across, and another dotted line going across. Well, because it's a parallelogram, we know that they bisect each other, but also there's a couple other things that we might notice. For instance, the angles formed by the diagonals are right angles. They cross and are perpendicular to each other. Second off, each of the diagonals seems to cut the opposite angles in half. Like this side and this side are congruent. Or that angle and that angle. Same with these two. So with a rhombus, there's a couple of extra special properties that happen because all the sides are congruent. We end up saying diagonals are perpendicular, and the diagonals bisect opposite angles. these are properties that the rectangle doesn't necessarily have. For instance, in a rectangle, the sides aren't all congruent, but we do know we've got 4 right angles here. All angles are congruent, and they're going to be 90 degrees. With a rectangle, the diagonals also aren't going to be perpendicular. I mean, take a look if I draw a rectangle over here. If I draw this rectangle here, and I draw the diagonals, these diagonals do not make right angles. Oops. How about that? These diagonals do not make right angles, but they are the same length. In a rectangle, the diagonals are congruent. Last, most certainly not least, a square actually follows the properties of both a rhombus and a rectangle. The sides are congruent, the angles are all congruent, so every one of the properties from this entire chart so far applies to a square. All the above. So this is what we're talking about in 7.4. Literally, this is basically the entire lesson. We will be talking about trapezoids and kites in 7.5, but for now, let's take a look at the actual notes and see what we can fill in. So we're going to do all these definitions, and then we're going to see how to use them. Let's start by talking about rhombuses. We know that rhombuses are a type of parallelogram. It's specifically a parallelogram with 4 congruent sides. A rectangle is similar. It's another parallelogram because we know that the opposite sides are parallel to each other. But this one has 4 congruent right angles. Finally, a square is both a rhombus and a rectangle according to our diagram. So we say that the definition of a square is a parallelogram with 4 congruent sides and 4 right angles. Nice. These next 3 definitions are corollaries. We recall that a corollary is just a theory that's based off of another theory. So, the rhombus corollary is based off of the definition of a rhombus, for instance. These corollaries are so similar to the definitions of the shapes that I'm okay if you use them interchangeably. For instance, the rhombus corollary says a quadrilateral, instead of saying a parallelogram, is a rhombus if and only if it has 4 congruent sides. So all this does is it takes this definition and makes it go both ways. If you see a quadrilateral and it has 4 congruent sides, it has to be a rhombus. You can probably predict the next one, but a quadrilateral is a rectangle if and only if it has 4 right angles. So any shape you see that has 4 right angles is a type of rectangle. Even squares are a type of rectangle. Speaking of, the last one's a bit weirder. It says a quadrilateral is a square if and only if it is both a rhombus and rectangle. So this corollary is based off of the definitions of a rhombus and a rectangle. If it fits this definition, has 4 congruent sides, and this definition has 4 right angles, only then is it a square. Last 3 definitions, and we're going to move on. Starting off, we have the rhombus diagonals theorem, which is actually one of the points that we mentioned over here. Didn't we say that the diagonals of a rhombus are perpendicular? That is the rhombus diagonals theorem. More specifically, the theorem says this. A parallelogram is a rhombus if and only if its diagonals are perpendicular. So that also means if you know something is a parallelogram and you see that it has perpendicular diagonals, it is required to be a rhombus. I could literally just draw this and say, make the parallelogram around this, and you would say, oh, Mr. Strager, it's a rhombus, because of the right angles here. Now, the rhombus opposite angles theorem is the one that said that all the little angles formed by the diagonals in a rhombus are congruent. For instance, this angle is the same as this angle, which is the same as this angle, which is the same as this angle. So in the opposite angles, the diagonals will bisect both of them. A parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. Each diagonal should cut the opposite angles exactly in half. The very last theorem for today is the rectangle diagonals theorem, which is the simplest one. It says that a parallelogram is a rectangle if and only if its diagonals are congruent. If 2 diagonals are the same length, let's say I told you that this diagonal and this diagonal are the exact same length, automatically you can say that the shape around it has to be a rectangle. So let's flip over to the back and see if we can use some of these. So for example 1, we're trying to figure out if these statements are, not only if they're true, but if they're ever true, or always true. Let me give you an example. In part A, it says, for a rhombus, QRST, Q has to be congruent to R. My suggestion for solving these problems is to try and draw an example of a rhombus where this is happening, and try and find a counterexample. So if I'm drawing a rhombus, I usually like to draw them like this, but you can draw them like diamonds if you'd like. Q, R, S, T. In this diagram, is Q congruent to R? No, Q doesn't look congruent to R in this, so it's not always true. There are some rhombuses where Q is not congruent to R. But we do need to see if it's sometimes true. So let's think of a counterexample. Is there a type of rhombus we could draw where Q and R are congruent? Because there is. What if we drew a rhombus that had 4 right angles? What would we call that? A square. If a rhombus is a square, because remember, squares are types of rhombuses, then this would work. So we would say it's sometimes true. Pause the video and see if you can take on exercises B and C in this example. Hopefully you've had a chance to give it a shot. Let's see what we can do. So for a rectangle ABCD, AB should equal CD. If I draw a rectangle with this type of example, well, of course AB and CD are congruent. Or sorry, their lengths should be equal. It's a rectangle, so no matter what, the opposite sides are congruent. No matter what type of rectangle I draw, even if I draw it as a square, the opposite sides are still congruent. This is always true, since I can't think of a single time this wouldn't work. For a rectangle DEFG, its diagonals are perpendicular. So again, I'm going to draw a rectangle. I'm going to draw the diagonals. Right off the bat, we can see an example where it's not true. So it's not always true, but is there a type of rectangle we could draw where the diagonals are perpendicular? Well, diagonals being perpendicular, as we discussed, is a trait that rhombuses have. That's the rhombus diagonals theorem. So if I could draw a rectangle that is also a rhombus, it would be sometimes true. A rectangle that is also a rhombus is another way of saying a square. So in a square, the diagonals are going to make right angles. It is sometimes true. Cool. Next up, we have example 2. For example 2, we are asked to solve for each of the numbered angles in the rhombus. Oh boy. Well, we have some good news here. Because we're told right out the gate this is a rhombus, there are certain properties of rhombuses that we can use to help us. For instance, right away, I'm looking at the measure of angle 3. Do we know what the measure of angle 3 is? Well, because it's a rhombus, we know that rhombuses have right angles where the diagonals cross. The measure of angle 3 should be a right angle. It's 90 degrees. Beyond that, we're sort of stuck until we see that this angle here, FEG, is this tiny angle, is 27 degrees. Don't we know something about the opposite angles of a rhombus? According to the rhombus opposite angles theorem, each diagonal bisects the pair of opposite angles. So, that means that if this side's 27, angle 4 is also 27. And since the angles are the same on both sides of a rhombus, that means angles 1 and 2 are also 27. So we've got some good stuff here. To figure out the measures of angles 6 and 5, there are a couple ways of doing it, but I want to teach you the shortcut. I want to redraw a triangle down here that goes from F to E and over to the middle. We know that all of these middle angles are supposed to be right angles, correct? So this is angle 5. This one's 27 degrees. To solve for angle 5, we can remember that all triangles must add to 180. We also know that in a right triangle, since this one's already 90, these last two have to add up to 90. So the measure of angle 5 plus 27 should equal 90. We found the measure of angle 5, if we subtract 27 from both sides, is 63, because that's the only way that this triangle adds up to 180 degrees. And of course, the measure of angle 6 can be solved in the same way. So there we go. I'd like you to pause the video here. I'm going to put up the answers for the other two, but I want you to really try these out and give it a shot. Pause the video and come back when you're ready to see the answers. How'd you do? These are the measures of all these angles in the rhombuses. Next up, example 3 is really where we put the pedal to the metal. We have to name each quadrilateral for which the statement is always true. So, it's very possible that if something works for a square, for instance, then it would also work for rhombuses, because a square is a type of rhombus. It would also work for rectangles, since squares are rectangles. It may work for parallelograms, because squares are parallelograms. We need to see what works for each of them. So, for part A, which of these shapes are equiangular? All the angles are the same. Well, not parallelograms, not rhombuses. We just did activities that showed that rhombuses don't have the same angles. Rectangles and squares, though, both have 90-degree angles. So this is a rectangle and square. For part B, for instance, where it says it's equiangular and equilateral, we know there's only one shape that fits, the square. Because a square is a rectangle, which means it's equiangular. A square is a rhombus, which means it's equilateral. None of the other shapes are both. Diagonals being perpendicular is a theorem that we just talked about with rhombuses. So no matter what, we know that rhombuses, or diamonds, have this trait. However, what is a type of rhombus? A square. So, whatever definitions work for a rhombus also work for a square. Opposite sides being congruent is a flashback. We've talked about this since 7.2. Parallelograms have opposite sides that are congruent. And since rhombuses, rectangles, and squares are all just types of parallelograms, all of them have opposite sides that are congruent. Same with the diagonals bisecting each other, right? I mean, that's part of the definition of a parallelogram. It's the parallelogram diagonals theorem. So once again, this is a parallelogram, rhombus, rectangle, and square, where the diagonals cut each other in half. But the diagonals bisecting opposite angles is much more specific. This is a theorem that we talked about just a second ago with the rhombus opposite angles theorem. The rhombus diagonals bisect the angles. So if it works for rhombuses, what other shape does it have to work for? Squares, because squares are a type of rhombus. Cool. Example 4 is a very quick example. We've done these before in the past. Finding the length of the diagonals, where one of the diagonals is this expression, and the other one is this expression. We know that the diagonals of a rectangle, according to the rectangle diagonals theorem, are congruent. So if the rectangle has congruent diagonals, that means that WY and XZ should equal each other. In other words, 16x plus 2 should equal 36x minus 6. I'd like you to try and solve this one on your own, and come back when you're done. Fair warning, you will get decimals. Pause the video and try this one out. We should get 8.4 for our answer. Very nice. Example 5 is a deceptively long problem. We're trying to decide whether the shape noted here is a rectangle, a rhombus, or a square. But we do know it's a parallelogram at least. And we have to give all the names that apply. For this problem, we always want to start by graphing each of the points. So 2, negative 6 is up here. That's where A will be. B is at 6, 8, so that's going to be all the way up here. There's B. C is at 4, 0. Easy enough. And D is at negative 4, negative 2. There we go. There we are. There we are. And there we go. Just from looking at it, we can tell this looks like a rhombus. But we need to be sure, and we need to prove it. Well, no matter what, this is a parallelogram. So we know, for instance, that AD has to be congruent to BC, and AB should be congruent to CD. We just need to see if these measurements are the same, right? If AD and AB are congruent, that means all 4 sides of this parallelogram are congruent, and it has to be a rhombus. So let's find the distance between AB and DA using our distance formula. To go from A to B, the two x values are 6 and negative 2. So I'll do 6 minus negative 2 squared plus the y values are 8 and 6 squared. 6 minus negative 2 is 8. Squared is 64. So this big part is 64. 8 minus 6 is 2. Squared is 4. So we have 64 plus 4. It's the square root of 68. Similarly, we can do the same thing for DA. D starts with negative 4. A has negative 2 in the x, so negative 4 minus negative 2 squared plus the y values are negative 2 and 6 squared. Negative 4 minus negative 2 is negative 2. When we square negative 2, we get 4, so this big piece is 4. Negative 2 minus 6 is negative 8. Squared is 64. So once again, you get 4 plus 64, it's 68. We know that all 4 of these side lengths are congruent to each other. So bare minimum, it's a rhombus. Rhombus, since all sides are congruent. But we're not done yet. We know from looking at the diagram that it's not a rectangle or a square, but we need to show that it's not a rectangle or a square mathematically. Well, what's in common between rectangles and squares? All 4 of the angles would have to be congruent, right? So if we really wanted to see if these angles are congruent, we would need to see if they're right angles. How do you know if 2 angles are right angles? You know something's a right angle if the lines are perpendicular. So we need to show that these 2 lines are not perpendicular. Anytime we're dealing with parallel or perpendicular, what we're really dealing with is the slope of the lines. So let's find the slope of AB and the slope of DA. To go from A to B, I'm going to use my green marker here. We go up 2 over 8. So the slope is 2 over 8, or 1/4. To go from D to A, we go up 8 over 2. Up 8 over 2 means the slope is 4, because 8 divided by 2 is 4. The only way two lines are make a right angle is if they're opposite reciprocals. And while 1/4 and 4/1 are reciprocals, they're not opposite reciprocals. It would have to be 1/4 and -4, for instance. That would make a right angle. Because they're not opposite reciprocals, do not form a right angle. Therefore, not a rectangle. Very nice. Thank you so much, everybody. This is going to conclude our notes for today. Have a fantastic rest of your day.